All right, I think I'm up and running. Let's get a full screen here. Okay. All right, so this video is an attempt on my part to connect the conversion process for many of the algorithms that we study, talk about them from some geometric perspectives and some unit conversion perspectives. And I hope that I do justice to the cause. All right, so we'll start with the easiest function, which is linear. And we generally don't put the one above the parentheses, but honestly, I think you can think about that one as a dimension. And as we work with shapes and squares and different types of rectangles and cubes, perfect cubes and cubes with different dimensions, different amounts of distances for length, width, and height, I think that this discipline has evolved from that study. I know there's a debate as has math evolved or has it always been there and it's just being discovered. I don't know. I've heard people chat about that a little bit. But from our standpoint, we're just trying to get the mechanics down. Some folks are having some trouble with that, and that's what this video is for, to help you improve your mechanics of those quick 10-second, give me a point on a curve, and if it's where the pattern emanates from, then how do you write the equations in 10 seconds or less? That's one of the goals of this. Let me clean the screen a little bit there. All right, so let's have at it. And we're going to work on linear, quadratic, square root, absolute value. I'll show you a cubic very quickly. I'll show you a trig conversion very quickly, just to show you that if you get the mechanics down in one place, it will allow you to see more clearly some of those other relationships. I feel like this is a little foggy here. Let's see if clean the screen a little bit here. The camera, I mean. Let's see if that helps. All right, well, hopefully it's my eyesight and not the camera. All right, so let's say that we have a line that is 5 units long, and I want to convert it to 3 units. Well, there's really 2 ways we do it in mathematics. The first is, well, let's just say that we get rid of it and build a new line. Erase it and then add 3. There you go. I just accomplished it because I got the marker. That's one way we do it. Another way we do it, or it can be done, I'm not saying we, shouldn't be saying we. Another way that I might do it is to say, okay, I want to turn this into 3 units. Well, I'll break it up into 5 parts. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yeah. And what I'll do is I'll take the line and I'll multiply it times 3/5. All right. This 5 indicating I broke it up into 5. What happens when I do that? I cancel that and I get that. I think it's a simple enough concept. In one instance, I use subtraction, and the other I use division. Those are very good operations for conversion. All right, so let's do an equation of a line through the points 3, 8, and 9, 15. And we're going to be counting from the number 3. What does it mean to count from the number 3? All right. Well, let's say that that's 3 units long. What if I went over to the number 4 for a length? I think I've changed things. I think I've changed things by 1 unit because I'm counting from here. And I think a statement like x minus 3 is very good for counting from the number 3. If I moved to the number 5, well, I've gone up 2 units. If I put the number 9 in there, I think I've gone up 6 units. 9 minus 3. I'm counting from the number 3. Then we could put it on the x-axis. Here's the number 3. If I move out here to the number 9, I have moved 6 units on a line. All right. All right, so what are the 5 things you have to do to count from the correspondence of 3 to 8, 9 to 15 if it's a linear conversion? Well, let's see. Let me start with the number 3. I think the first thing I do is make a ruler, a symbolic ruler that counts from that number. And if I put 3 into this, I haven't moved at all. There's no movement. And if I want 8 of something, I can do that. So there's your first 2 steps. Get rid of the first number. We did. With that calculation, bring in the second number. We're doing 2 things. Next, I see the number 9. I recognize something. I recognize 6 units of change. All right, so we're going to work with that. We're going to work with that 6 units. We're going to cancel it out because the change from 8 to 15 appears to be 7. 4 easy steps. We'll do them again here in a second. How do I find out if it's very early in the morning and I'm awake and I didn't make a calculation error, which quite frankly, I'm doing more and more of as I get older? I'll drop the 9 in. And I see 9 minus 3 is 6. We just talked about that cancellation. Remember, 6 is divided by 1 and multiplication is commutative. So maybe you can see it more clearly this way. The 6's divide out to be the number 1. 7 times 1 is 7 plus 8 is 15. 4 easy steps and I'm done. And I want to keep this moving quickly, so I'm not going to talk too much, but let's do another one. Let's do -3, and I'm just going to start with that number. Remember, this is an input, output, so I probably should put something equals y here if I really want to do justice to the cause. I'm starting with -3 this time, and now we're just working with numbers. I need to change that number into the number 8. So I've got a marker. I'll start with -3. Why don't I add 3? Because it's gone now. And materializing the number 8 is simply writing it. It's 2 steps. Then I look and I say, well, boy, there's change here from -3 to 9 of 12 units. But I only want what? I want positive 8 to -11. I think that's down 19. And so let's go back to step 3. Step 1, -3. Step 2, writing the 8. Of course, I forgot what number I had there. I'll talk about it. So -3 to 9, okay, is 12 units of change. So I get rid of that 12 units, and I went from 8 to what, -11? Is that what I wrote originally? Well, if it wasn't, sorry, 8 to -11, down 19. Equation of line. Now let's turn our attention to a different calculation, squaring. But let's use some of the same principles. Same 4-step principles. I'm counting from the number 3. All right, which in this case is a side length. It's still a length. This is still linear, but I'm converting it into what area? Well, I think I can do that. I think I can say, okay, I start with a 3. Well, I think I can say x minus 3. But I'm squaring. I've got one more calculation involved in this process. So this is a quadratic calculation. And therefore, what do? I want 9. Same thing, I write it. I've only done one different thing. Recognizing that it's a quadratic, which is a cup-shaped graph up or down, depending upon the change in y. Right? But what is the change from 3 to 5? Well, it's not linear. This is linear change. But I'm after quadratic change. So when I put 5 in, 5 minus 3 squared represents area. Represents this area. All right, and 5 minus 3 squared is 2. I'm sorry, 5 minus 3 is 2, squared is 4. All right, so when I put the number 5 here, I'm creating quadratic change. It's no longer x to the 1. The major operation is x to the 2. But I'm measuring from the number 3. So I get 4 units of area change, but I didn't get 4 units of area change. from 9 to 25, I got 16 units of area change, right? So if I drop the number 5 in, 5 minus 3, 2 squared is 4. I get rid of the 4s, and 16 plus 9 is now 25, which is area over here. The y value represents area. So I'm getting 4 times what should have happened. Because if I increase a line by 2, I should get 4 units of change, but instead I got 16 units of change, which means I have to multiply this times 4, this process. That was a little awkward, but let's just talk about it, the mechanics. If I said something that, because it is, it's very early here, it's still dark outside. So let's just randomly pick some numbers. Let's say a 7 gets you 2 and a 12 gets you 100. And what are the 4 steps for quadratic change? Quad, 4 sides of a rectangle. In this case, we're working with squares. Step 1. Let me write this down here. Obviously, tell my memory is starting to disappear as I speak. All right, so I've got it here to remind myself what numbers I put down. So you're going to try to do this now on your own. What do you do if you see the number 7? Hope you right, it's minus 7, and if it's a squared problem, I hope you remember to put the square there. And we're going to get 2 units of area. Here we go, and I will put a big A for area, and I probably could put an S here for side length, but you work with what in math, X's and Y's, and you remember that they're supposed to stand for something, depending upon what you're studying. And then we go to 12. Well, what's the change? What is the change? It's not linear change, it's quadratic change. And what's the quadratic change? I believe I'm looking at 25 units of quadratic change. But then you look at the change you want. The change I want is from 2 to 100. I need 98 units of change. Okay, I think that's been in one textbook that I've seen over the years, but it should be in them all. It only takes 10 seconds. You study this for a couple of days in a row, a few minutes each day, and you should be able to do that. Now let's do one more. Well, I think I got one over here. Looks like I've got a relationship over here. Of course, you definitely need to understand the squaring process to a certain extent, right? Right? 0 times 0 is 0. That's where you get a minimum. Right? So, I mean, that's happening in this process as well. 1 times 1 is 1, 2 times 2 is 4, 3 times 3 is 9. Hope you can see the acceleration as we move to the right. But we're not starting from 0, but we're creating it by doing what? By writing x minus 3. It's really measuring change from the number 3, squared change from 3. Right? So if you're on a xy axis, here's 3. If I move over to 5, what's the square change? The square change is really 4 units of area. All right. Hopefully that makes some sense. So if I drop a 3 in, I get a 10. And if I want to get a 10, I write it. And so our area statements are over here. And then I go from 3 to 5, which is again 4 units of change. Well, what did I want? 10 to 101, 91 units of change. That would be that graph. You throw it in a calculator or a computer and graph it. You'd see that it has a minimum of 10 units and 101, right? So you get the roots of that now in 10 seconds or less too, but that's another discussion. Okay, so let's try one more practice here. All right, so 267 to 03. You try it, pause the video. I'm just going to write it. I'm measuring from 2. What? Yeah, I should have thrown a negative in. So if this was -2, you would have written x plus 2. I haven't done that enough in this video, but we've already put it in here. So let's go. So x minus 2 squared, I write 67. I look at the square change, even though I'm going back 2. I'm squaring it, so I think I like the number 4 too much today. And now from 67 to 3 is minus 64. And if you were to multiply that out, you would get minus 16x squared plus 64x plus 3. So if I had a marker 3 feet high and I threw it up and 2 seconds later it reached its maximum height of 67, then you could study initial velocity, you could study gravity, and now we're into physics. Okay, very quickly writing that. Okay, so now how about square root? Let's talk about a square root function. And what I'm basically doing, over here, g of x equals x squared. So now h of x equals the square root of x is our major operation. We're really starting to create a template here. So we've got g of x plus, why don't I say c, some constant, maybe k. I tell my grandson k for cat, K-A-T, keeps telling me it's C-A-T, I keep telling him he's wrong. So let's do justice to the cause. So let's say we have f of x. So this was h of x, huh? H of x, this is h of x. F of x, the linear function. X to the 1, right? That's what the function was. The function really was an x to the first power with a little bit of multiplication and an initial condition of sorts. Okay, so that's kind of following that format. G of x. G of x was squaring. Basically writing this basic template where g of x was some kind of squaring as the major operation. And h of x, square rooting, you probably can guess. Some kind of major operation. Right? And we're going to build off of those important places. All right, so what do we have here? We have y values coming from, well, square root's actually a length. Right, it's a length. So I'm not starting with 3 and 5, I'm starting with 9 and starting with 25. The areas bring me back to the square roots. So how would I measure this? Well, major operation, I don't need parentheses. No, we're really doing the same thing, x minus 9, but I don't need the parentheses here because the square root symbol acts like a parentheses as well. So I'm putting in an area of 9, and if I did that, square root of 0, okay, here's squaring, right? How small can I get? Oh, that square root smaller, that square root smaller, that square root smaller. I can go to 0. So I make it a measurement from 9. So I'm going to measure from change from 9. So it's really saying that if I put a 9 in, I haven't moved from 9, so it's now 0. I get a side length of 3. If I put 29 in, 25. If I drop a 25 in, I get 16, but the square root of 16 is 4. So I cancel out that 4 again. And now what am I looking at? The change in the length, 2 units. And so that would be that graph. So if I started at 9.3, let's just do some quick estimating. Let's call that 9, let's call that 3. I want to have too many concepts here. 25, way out here. I'm going to 5, which is about this change based on what I'm looking at. So slow change, square root change. That's really one of the branches of y equals x squared, right? And then there'd be some discussions about what a function is and everything else, but don't want to complicate this too much. Just really want to get down to just the mechanics of how you write these equations. And so let's give you a chance now to try some random numbers. Let's say I have a square root function from, let's go 4, 7, and let's go negative 4, 7, negative 4, 7 to, how about 11, 20? All right, you pause the video and you try to write that equation. Since you've already paused it and had your moment, I'm just going to keep going. So I see the square root of x plus 4. That's the first x, the most important one, where the pattern emanates from. Initial condition is 7. I can drop an 11 in there, and if I do, I get the square root of 15. That's what's going to cancel out. And how do I get from 7 to 20? 13. Get it in one place, you get it in them all. All right, then let's look at the absolute value of x. Measures distance from 0. Right, so the absolute value takes the line y equals x. This is the line y equals x. I hope you can see that your x's equal your y's. And what happens when I slap an absolute value on it? Well, the negatives become positive and we get a V shape. So absolute value graphs are V-shaped graphs, and they're either up or down, just like the quadratic. And so if we start with an absolute value, let's put values in here. Let's put, how about we start with a -7 gets us 20. And how about we go over here to 1 gets us 37. Okay, not drawing the scale, well, maybe it is. All right, so what do we do? Well, I see a pattern emanating from this coordinate. So I'm going to highlight that coordinate with the major operation that I'm seeing. What's the major operation? Sure looks like absolute value to me. So you pause the video, see if you can write that. I'm going to write x plus 7. Measures linear change from -7, that does. Then I'm going to put in the major operation. And if I want to get 20, they are now linked. And I measure change, looking from -7 to 1. That's 8 units of change, absolute value, really, right? And that's canceling that operation. But the absolute value of 8 is 8, so I'll just leave it there. And how do I get from 20 to 37? 17. And we'll do one with a negative. And just so I can show the absolute value. So let's go from -5 gets me 30. And let's go over here to -11. And let's say we drop down 40 units to -10. All right, so you pause the video and you try to write that. I'm seeing absolute value. I'm seeing a V-shaped graph. I'm going to measure from -5. So I've got x plus 5. I'm now measuring absolute value change from -5. What is the absolute value change from -5 to -11? It's actually 6 units because I'm really doing the absolute value change from -11 to -5. All right, -11 plus 5 is 6, -6, but the absolute value of -6 is 6. So it's still absolute value is positive change. And I'm going from 30. Going from 30 to -10, I've gone down 40. And if I do that, from what? I forgot to write the 30 over here. All right, that should be the calculation that gives you this graph. Let's put -11 in, see how it works. -11 plus 5, -6. What's the absolute value of -6? 6, these cancel, -40 plus 30, -10. And as you're learning this, you should perform those calculations. Almost done here. Then I'm going to show you some advanced conversions. But what we're basically doing is we're working with these functions, linear, quadratic. I'll do a cubic for you from the polynomial standpoint. Not sure this is a whole nother discussion, actually. But if you study these from written in this form, then minus b over a, minus b over 2a, minus b over 3a, minus b over whatever dimensions. I can only draw something on the board that has 3 dimensions. I can only represent it. I can represent a line. I can represent area. And I can represent cubics with what? A line, area with rectangles, cubics with cubes. Oh, that's a great drawing of a cube. Right, boom, 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 boom. But you get the idea, right? I can draw those things so I can see what's going on. And then I can extrapolate to higher degree polynomials and write whatever you want in graphing form. I don't think it's useful. At least I haven't found a use for it for 5th and 6th and 7th degree graphs to be, written in graphing form. But who knows? Maybe there are some usages for it. But let's actually use those principles of conversion, the average of the roots, and actually look at a cubic and see how much we can write about it with looking at some of the other videos that explain what I'm about to do. So I can definitely see that I'm going down at 10 to 1 at a height of 5. I'm going down 10 to 1 at a height of 5, minus b over 3a, minus b over 3a being my point of inflection, which is 6 divided by 6, which is x equals 1. So at x equals 1, this is turning very quickly. So I'm going to get rid of the x-axis because I don't know any values at the moment. But this is 0, 5. And my slope at that instant is negative 10. If I drop in a 1, I get 2 minus 6 minus 10 plus 5 for a y value. There's a 3 to 1 relationship in the cubic at the point of inflection and opposite. So that becomes minus 4, minus 4, minus 14, minus 14 plus 5 is negative 11. So 1, negative 11 is where this thing has a point of inflection. So now I got to find my maxes and my mins. So at negative 11, c minus 3a h squared is going to be the slope at that instant, which is equal to minus 10 minus 3. Don't make any mistakes here, Jim. 2 and 1 squared. So that looks to be minus 16. I'm going down quickest right here. My slope is equal to minus 16. So it looks like I'm going to look something like this. All right, point of inflection. And if I want to find that, I can do that x value comes from, let me remember, h minus the square root of minus m over 3a. All right, so that's the x value. I'm probably not going to drop that x value into the equation to find the y, but I'll just do it quickly. H is positive 1 because this can be, well, I'm not going to write it in symbolic form. And where was it? Minus the square root of minus a minus 16 all over 3 times a, which is 6. 3 times 2 is 6. And so this is 1 minus 4 over root 6. Okay, minus the minus 16, 16, square root of 16, 4, I can write it that way. And what is 4 over root 6? I don't know. Root 6 is between root 4 and root 9, right? So it's between 2 and 3 units. So between 2, if it's 2 units, then it's 1 minus 2. And if it's 3 units, it's, well, it's 1 minus 4. Ugh, whatever. You can get an approximation. It's too early in the morning here for me to do that. But it will allow us to see that cubic without a calculator very quickly and very easily. All right, and then we can use these principles of conversion to write trigonometric functions quickly and easily. All right, so in future studies, you're going to look at the circumference of a unit circle. So it's 2 pi units around, which is 6.28. So why do we use this? It's better for applications. So here we have an angle, right? You're used to looking at angles written that way, but isn't that just an extension of, isn't that just an arc length? Okay, so if let me just write this rather than, there are videos that explain it. So I'm just going to write this quickly using a sine function. So I'm measuring from 45, things go up and down from 45. How much do they go up and down from 45? 5 units. And you'll study the sine function in future classes, as in ours after midterm. And so where am I headed? I'm headed to writing 1900 as pi over 2. Okay, well, that's not hard. X minus 1900 gets me pi over 2. Pi over 2 is 1/4 of the way around this circumference, 1.57 roughly radius lengths. Here's a radius length. There's one. Just put some thoughts in your heads. There's one radius length, about 57 degrees, and then a half takes us basically to the top, which is a maximum, and I'm measuring from a maximum. And so now what happens? I go once around the circle. Once around the circle is 2 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, 6 pi, 7 pi, 7 pi. And how many years did it take? 1900 to 2024, 124 years. And now I'm writing trig functions quickly. Based on what? The study you're working on over here, linear functions. You got to get this down. in order to understand what I did over there. All right, and so I just put some things in your head. All right, I'm on a roll now. I'm rambling. Time to get my coffee. Time to really wake up. Time to plan today's class. And I'll see you there in about, whoo, about 9 hours. Okay, ciao. Let's see, how do I end this thing? Am I even recording? Yes. Oh, there it is. Got to get glasses.